These notes are going to go through what's called the kinetic molecular theory. They are simply notes. You certainly can obtain them from your textbook just as easily as you can from watching this video, but there are things that you've got to know. So we're going to go through these assumptions for the kinetic molecular theory and how they relate to gases. The answer to this riddle? They didn't necessarily play against each other. So remember, molecules of a gas are separated by very large distances, and that's a really important point when we're thinking of the kinetic molecular theory. So we're going to look at properties of different gases. The first thing, remember, they do not have a specific shape or volume. They expand to fill the entire container, and they take the shape of whatever that container is. They expand and contract with ease, meaning we can squeeze them to a certain extent. Balloons are another example of a flexible material that when you allow them to warm up or cool off, the size of the balloon will alter. They exert pressure, which is proportional to their number of molecules. So if you, again, think of a balloon, the more air molecules that we put into the balloon, the larger the balloon gets. That is because they're putting increased pressure, and to equalize atmospheric pressure, the end result is to increase the volume. More molecules is going to mean higher pressure. The density of gas is less than the same sample as a solid or liquid. That is because the gas takes up a very large volume, and since volume is in the denominator of the density formula, it's inversely proportional.
Alright, so here's what's happening. There's a gas inside this tank. It's called sulfur hexafluoride. It's a super heavy gas. Sulfur hexafluoride. It's boring. It's inert.
Anybody ask where I'm
It's odorless. Okay, so it's normally boring, but here, watch this. I'm going to slowly pull the lid off.
Okay.
So that should be perfect. Gary, would you take that little end off over there as well? You see that? Yeah?
Yes.
Alright, so let's see if, it feels pretty good. So let's see if we can float the boat. Okay? Ready? So here we go. Let's see if we can float the boat. Stay there, little guy. Tell me that's not amazing.
That is awesome.
Magic is, so is that, it's okay. Push it around. It's okay.
Crazy.
So this heavy gas is about 6 times heavier than the air that we breathe. And so I just have it coming through a tube here. And so I'm going to give us just a little bit more so you can kind of see what's going on. Here's what they use it for. Electrical engineers will flood a room or, part of a semiconductor or something with this material because it doesn't allow electricity it doesn't conduct electricity. So here's a taser. Okay?
Yeah.
So all right, so look. So when I put the taser down inside here, watch this. When I put it down inside, it stops.
Oh, it stops working.
And then when I bring it back out again, so they will keep it. So if you don't want something arcing from one place to another. But the coolest thing is this: because it's inert, you can breathe it, and you might see something different. Ready? So you just stick your head way down inside and breathe in. Breathe in. Ready? Now talk to the nice people. Try it. Come here. Get in there.
Awesome.
All right. So, Amelia, Becky, get in here. Kyle, get in here.
That is awesome.
Ready? So breathe it in. Take a big. Don't waste it. All right. There you go. Now talk.
So sexy when you talk like that.
Oh my goodness.
Now
All right. There you go. Ready?
Hello, everybody.
Come on. Now, ready? Breathe out so you don't die. Here, breathe in. See, now we're okay?
Now we're okay. Yeah.
One more time. Come on.
Barry White. I love it. It's a little Barry White voice. Okay, we're going to be right back, shall we?
I love this. Wow.
All right, fun little video there, sulfur hexafluoride. On to the kinetic molecular theory. First, we say that there's no attractive or repulsive forces between the gas particles. Remember, these are our intermolecular forces, and so with gases, we just pretend that they're not there. They do exist, as I'll tell you in a moment, but they're very, very weak. With gases, they're in the gas phase because they don't have very strong attractions. Volume of the gas particles is 0. In actuality, that particle itself is not 0, but when you compare it to the overall size of the entire container, The amount of space that the particles take up if you were to squeeze them all down into a small corner is very, very minimal. And so rather than applying a correction factor, it's just easier to say that they don't have any volume. The gas molecules are always moving, constant, rapid, straight line motion. They don't see something coming and swerve to miss it. They just straight on, run into it, bounce off, and head in the other direction. Collisions with the walls of the containers is what accounts for the pressure. And so if they were able to kind of curve to the side, they would never hit the wall of the container. We wouldn't have gas pressure. The more molecules you have, the greater the pressure is going to be because there's more collisions with the wall of the container. Collisions between gas particles are completely elastic. So two gas particles coming in towards each other, they hit each other, they bounce, and they go completely back in the opposite direction. They rebound, kind of like underwear. You pull it, you let go, boing, goes back to its original shape. Same idea, similar idea. No net loss of energy. So they hit each other, they collide, they bounce right back off. The temperature of the gas is measured as the average kinetic energy of the particles. We have mentioned that already. Low kinetic energy, low temperature. High kinetic energy, those particles are moving around really, really fast. Again, able to bounce into each other, causing friction, heating up, therefore the temperature is higher. Back to this picture again, we said the one on the left, the particles aren't moving very fast, and so it does not cause the red liquid to heat up, which does not cause it to expand. Picture on the right, we've got a lot of vibrations going on there, and so the liquid is able to expand when the particles are moving faster. So three variables that are always related to the gases: volume, temperature, and pressure. And then, of course, moles, which we've talked about before, is going to always give you an idea of how many particles are there. When we look at pressure, it measures the number of collisions with the walls of its containers. The SI unit, which is System International, is Pascal, but typically we want to be using kilopascals. The other unit we can use is atmospheres, and standard pressure in atmospheres is 1. Another unit you may see once in a while is millimeters of mercury. The standard pressure in millimeters of mercury is 760. Pressure is measured with a barometer, and that's what the picture is over there on the right-hand side. That is a barometer. Pressure conversions. You can use Table A. That is where you'll find all your values for your standard pressures. And you can use a small little fence. How many atmospheres are in 195 kPa? Let me find my pen here. So 195 kilopascals. We're going to put that into a fence, and we're going to use this relationship right here. We know that we have to cancel down into the bottom of our fence with our unit, so the 101 kPa goes into the bottom, and then I'm going to put 1 atm up here on the top. The answer to that is 1.92, and your unit is atmospheres, atm. Volume is another thing we want to be able to measure about gases. The SI unit is cubic meters, and 1 cubic centimeter is going to be equal to 1 milliliter, or 1 cubic meter will be equal to 1 liter. Temperature, we're going to have to use Kelvin at all times. The reason for that is that the Celsius scale can be a negative number, and if you're doing a calculation and you use a negative number, it will incorrectly skew your answer. So you want to be using temperature conversion we talked about prior to this. If we have 35 degrees Celsius, in order to get to kelvins, we're going to add 273 to that, and we're going to get 308 kelvins. And you're going to always want to use the Kelvin scale when you're doing any kind of calculations using the gas laws.